Welcome to Digital Electronics lecture series. This is lecture number 21 and we'll be doing arithmetic circuits which can do arithmetic operations. You start with the very first, half adder. So half adder is a combination logic circuit which can add two 1-bit numbers. It can add two 1-bit numbers. So here this is the block diagram. So here we have two inputs, A and B are the inputs, 1-bit numbers, two 1-bit numbers, and we have sum and carry. These are the two outputs. So we see this is the truth table of a half adder. So we have two inputs. These are two inputs. These two, A and B are the inputs, and we have sum and carry as the outputs. The first case, because we have two inputs, we have four combinations. So first input 0 plus 0, sum is 0, carry is 0. Then 0 plus 1, sum is 1, carry is 0. 1 plus 0 is also 1 and carry is 0. 1 plus 1, sum is 0 and carry is 1. See how it is this one. So last case 1 plus 1. So 1 plus 1, we have 0 and we have a carry 1. So this is the sum and this is the carry. So now we need to design a circuit for this. So let us first see only sum. Okay, for the sum part, okay, what we see for the sum part is that when these two inputs are 0 0, we have 0. For 0 1 we have 1. For 1 0 we have 1, and for 1 1 we have 0. So do we have any logic gate which follows this particular sum operation? So it is, we see for XOR gate. For XOR gate 0 0 is 0, 0 1 is 1, 1 0 is 1, and 1 1 is 0. Then let us take the case for carry. If you want to design carry operation, so for which gate we have 0 0 is 0 and 0 1 is 0, 1 0 is also 0, and 1 1 is 1. So we have AND gate. So AND gate follows this particular carry function. Okay. So we need two gates. One is the XOR gate, other is the AND gate. So this is how we design this is the half adder design. Okay. So this input A and B, they are given to XOR gate. Here we have sum, and here this is for the carry. So this is sum and carry. So this is jumper here. It shows that these two wires, this is not connected here. Okay. So this is how a half adder works. Now there is a drawback of half adder. What the drawback of half adder is that, suppose if you want to add two numbers like A0, A1, A2, A3, a 4-bit number, B1, B2, B3. So for adding this 4-bit number, we require 4 half adders. One for this A0, B0, second for A1, B1, third for A2, B2, and fourth for A3, B3. So if we use 4 half adders, of course we will get sum. Okay, suppose this sum is S0, and we may or may not get a carry. Suppose if we get a carry and carry comes, we have to carry the carry in the next place. So half adder only has provision to add 2-bit numbers. So this carry won't be added, and the sum which we get here will be the sum of A1, B1, but carry which was generated by previous addition will not be added. So this is the drawback. So half adder can only be used to add the rightmost bit, we can say least significant bits, but not the other bits, because if carry is generated, then that carry won't be added. So to overcome this drawback, we have full adder. So here we have full adder circuit. So full adder is a combination logic circuit which has 3 inputs and 2 outputs. So A, B input, and this Cin is the carry generated by the previous additions. So we have 3 inputs, outputs, there are 2 outputs, sum and carry. Now let us see the truth table of a full adder. So because we have 3 inputs, so we can make 8 combinations. So 0 1 0 1 0 1, then 0 0 1 1 0 0 1 1 4 0 4 1. So first 0 plus 0 plus 0, sum is 0, carry is 0. Then 0 plus 0 plus 1. So 0 plus 0 is 0, 0 plus 1 is sum is 1, carry is 0. Same way for this one. This particular case, we see in this case we have 2 ones. So 0 plus 1 is 1, then this 1 plus 1, 0, carry 1. Okay, so same way. So if we observe properly, wherever there are 2 ones, we get sum is 0 and carry is 1. And in the final case, we have 3 ones. So 1 plus 1, 0, carry 1. Then 0 plus 1 is 1. So sum is 1 and carry is also 1. So this is the truth table for a full adder. Now in order to design this, we have this particular circuit diagram. So here we have 3 inputs A, B and Cin, and we require 2 XOR gates, 2 AND gates and a OR gate finally. So this output is the sum and this is the carry out. So this is how we have designed a full adder circuit. Now we'll see another way of designing a full adder. We use the same truth table. So previously we saw we have directly do the full adder. Now we'll design it using K-maps. So here this is the truth table. We have sum and carry. So we know there are 2 inputs, so we need 2 K-maps, one for sum, one for carry. So this is actually, this will be a 3 variable K-map. So here I have drawn it for sum. So for sum, this is the K-map for sum. This one is the K-map for sum. A bar, B bar, Cin bar, so it is 0. Then A bar, B bar, Cin is 1 and so on. So we get this is what we get for the K-map for sum. Then we also draw the K-map for carry. So this outputs, these are the inputs. So this is the K-map for carry, A bar, B bar, A bar, B, A, B, B and this one. So here this is the K-map for carry and this is the K-map for sum. So let us solve for sum. So for sum we observe that we don't find any octet quads or pairs. So we need to circle the ones. So this is 1, this one, this one and this one. So now we write the equation for the sum. So equation for the sum would be, the equation for the sum is first this, the equation of this one is A bar, B bar, Cin. Then the next sum, I am writing a SOP equation because it is SOP K-map. So equation for this particular is A bar, B, Cin bar. Then the next, this one, A, B, Cin. And the last single one, this one, A, B bar, Cin bar. So this is the equation. Okay. Next we write the equation for the carry. Now in case of carry we see there are 3 pairs actually. This is one pair, this is another pair and this is the third pair. So we have 3 pairs. So this get reduced. So we have the equation for the carry. So carry is, we write the equation for this particular pair. So it reduces, eliminates one variable. So we have BCin, or the equation of this particular is AB, and this last pair is ACin. So now because we got 2 equations here and both are SOP equation. For SOP we know we require AND OR combination. So this is the final diagram. This is the final circuit. Okay. This is the final circuit diagram. Okay. And this diagram is what we have. So here the first part, you can see the first part is the upper part shows the sum. Okay, that is A bar, B bar, Cin, A bar, B, Cin, A, B bar, C bar n. Okay, and this is the last one. So there are 4, we require 4 AND gates. Okay, you can see here there are 4 AND gates and then final OR, and then for this case we require 2 input AND gates. So this is the equation for carry. So this is the output. This is how we design a full adder. Next we have the half subtractor circuit. So half subtractor circuit, as we see the block diagram, it has 2 inputs and 2 outputs. A and B are the inputs, and difference and borrow. D means difference, B, O means borrow. So these 2 are the outputs. So let us see the truth table of this half adder. This is the truth table of the half adder. These are the 2 inputs. So 2 inputs make 4 combinations: 0, 0, 0, 1, 1, 0, 1, 1. So first is 0 minus 0 is of course 0. Difference is 0, borrow is 0. Now what about 0 minus 1? Now see, 0 minus 1 is 1, because if we do this 0 minus 1, now 0 cannot be subtracted, so we need to borrow 1. So because of which we put borrow 1 here, because we taken borrow 1. Now borrow makes 1 0. Okay, borrow makes this number as 1 0. So 1 0 minus 1 is 1, because 1 0 in binary actually in decimals is 2. 2 minus 1 is 1. So therefore difference is 1 and borrow is 1. This is the logic. Then of course 1 minus 1 is difference, 0 is borrow. Then 1 minus 1, of course difference is 0, borrow is also 0. So how to design this circuit? Now designing the circuit part is for difference we see 0 0, which particular gate works in this way, that for 0 0 output is 0, for 0 1 output is 1, 1 0 output is 1, and 1 1 output is 0. So we see XOR gate. Okay, so what we observe is, to implement difference we need a XOR gate. So how the XOR gate, we write the equation for the XOR gate, that is for difference. So for difference purpose, for difference D, we require A XOR B, so we require XOR gate. Now regarding borrow, we see we only have 1 at the borrow at this point, at this input, and this input combination is 0 1. So it means the equation for borrow would be, for A we have 0 and B we have 1, so A 0, it makes A bar dot A bar and B. So these are the two equations of the circuit half adder, half subtractor. So this is the diagram, this is the circuit diagram. A B we have XOR, and for this A bar dot A bar and B, so we have this A bar and B. So this is the circuit diagram of the half subtractor. So there is a drawback of half subtractor. The drawback is that half subtractor can only be used to subtract two 1-bit numbers. Suppose if we have 4 1-bit numbers, and if a carry is generated by a borrow is generated by a previous subtraction, so that borrow cannot be subtracted. Okay, so in order to do that, we require a full subtractor. So full subtractor, as we can see the block diagram, it has 3 inputs and 2 outputs, A, B and BIN. BIN is a borrow in from the previous subtraction, and this D is the difference, and borrow out. Okay, so we have borrow in and borrow out, and this is the truth table. This is the truth table of a full subtractor, 3 inputs. So how does it work? 0 minus 0 minus 0. So these are the two outputs, 0 0. Then 0 minus 0 is 0, 0 minus 1, 1 is difference, 1 is borrow. Then again 0 minus 1, 1 is difference, 1 is borrow. So 0 difference, 0 minus 0 is 0. So this is what we get, 1 1. Then 0 minus 1, 0 minus 1, 1 is difference and 1 is borrow. Then that minus 1 minus 1, whatever we get, the difference becomes 0, and this becomes borrow out, becomes 1. Okay, so because when we do 0 minus 1, we have 1 is difference and 1 is borrow. Okay, so and that we again subtract with 1, because difference is 1, so that 1 minus 1, again difference becomes 0. Okay, so this is 1, 0 1 1 is 0 1. Same way we can check for all the other entries. Okay, again last one, 1 minus 1 0, and 0 minus 1, 1 is difference, 1 is borrow. So this is the truth table. Now we can draw, as we have to implement this circuit, we need to draw two K maps, one for difference, one for borrow out. So these are the K maps. This is the first K map. This is the K map for the difference. You can check this by using paper and pen and draw that particular truth table. Now we write the after drawing this, we see there are no chords, no octets, no pairs. So we need to encircle this. So I just encircle them. This is the first 0, 1, the second, the third, and the fourth one. So this is what we have. So we write the equation of difference. So I just write DIFF. Difference is first the equation of this one, this one. So this is A bar, B bar, and BIN. Then the second, this one is A bar, B, BIN bar. Then the third one, this one, A, B, BIN. This is A, B, BIN, and the last one is this one, A, B bar, BIN bar, A, B bar, A, B bar, BIN bar. So this is the equation. Okay, this is a SOP equation, so you require AND OR logic that will draw afterwards. Then next is for borrow. This is the for borrow. Now in case of borrow, we find there are 3 pairs rather. We get 3 pairs here in this case. Okay, so this is one pair. So this is one pair, this is one pair, this is second pair, and this is the third pair. So we get 3 pairs in this case. Now we write the equation for the pairs. So the equation for the K map. So this is borrow. I write BO. So this is first pair. The equation of the first pair is A bar CIN bar, or this one, then this is A bar B, and the last one is BCIN. So these are the 2 equations. Now we'll see how to implement them using AND OR logic. So here is the circuit diagram, AND OR logic. So for difference we have 4 sum of products terms, SOP terms. So first term is A bar B bar BIN, then we have A bar B BIN bar, then A B BIN bar, A B bar BIN bar. So they are connected to AND gate, and then for finally OR gate, and this is the difference we get. Then for borrow we have 3 SOP equation, 3 SOP terms. First is A bar BIN, A bar B BIN. So they are connected to AND gate, and then finally the OR gate. So this is how we design the full subtractor. Okay. So that's all for this session. Thanks for watching.